Okay, our next speaker is Hugo. Will be giving us an update on the Sunburst project. Thanks, Hugo.
Thank you. Hello, everyone. So I'm Hugo. I'm a hardware software engineer at lowRISC, a very vague title, but I do end up doing an awful lot of random stuff. So I guess it kind of fits. And I'm going to be presenting one of the projects we've been working on that was funded by the UK government called the Sunburst Project. So we've just finished phase 2. So I'm going to talk about the results and that have come out of it. So to start off, who has heard of lowRISC? Oh, that's pretty good. We were founded in 2014 out of the University of Cambridge Computing Lab. We're a non-profit, and our mission is to drive commercial adoption of open source silicon. We've got a full stack engineering team, so we do hardware design, verification, and we've also got compiler and software engineers. We were one of the founding members of the RISC-V, RISC-V International, and we're also a founding member of the CHERI Alliance. We've got an office in Cambridge and Zurich, so if you're interested in a job, we are hiring. So for the last decade, most of our efforts have been in the OpenTitan project. Who here has heard of OpenTitan? Nice. Who's used OpenTitan hardware? That's pretty good. So yes, OpenTitan. It's a project to produce a high-quality reference design for a root of trust and integration guidelines. We do this with a bunch of amazing partners. So we're just the non-profit kind of steward, and then loads of for-profit companies work with us to make it a reality. There are two tops. There's the Earl Grey, which is a discrete chip that stands on its own. And then there's this new integrated top that's made its way into the repo this year to be integrated in larger SoCs. And it's all Apache 2 licensed. So if any of these blocks look interesting to you, like the Ibex Core is very popular, OTBN's cool, USB device is really nice because they're not fun to make, do take it. And we have silicon now. So it's been a long time coming, but there's silicon. It's production quality, and yeah, production pieces already. Google said that's going to go into Chromebooks that are coming later this year. So you'll be able to buy open source silicon, which is awesome. And it's also going to go into their data centers. And then on the integrated side, Revos is a startup. They're making server class, high performance SoCs. And they've said they're going to use it inside. They've already started putting it inside their designs. So the Ibex is the core of OpenTitan. It's a RISC-V 32-bit RISC-V core, very configurable. It came from the Pulp project, and then they gave it to us, and we maintain it and add a lot of DV as part of the OpenTitan project. And then this leads nicely onto the talk today. Microsoft took it because they used it and added and implemented their new ISA, CHERIoT. So to start, CHERI. Has anyone here heard of CHERI? Oh, good. That's good numbers. So CHERI is been in research for about 15 years now. It stands for Capability Hardware Enhanced RISC Instructions. Basically, in a normal computer, you point to an address and you can grab anything from that address, right? And you might have some MPUs and stuff. CHERI adds some information to around where the pointer is stored that gives you a top and bottom bound. So if you're giving an array to someone, you can bound it, and you can also add permissions to it. So it allows you to build these least privileged, fine-grained, memory-protected systems, a super scalable compartmentalization to the language level, so you can between functions, and it works with existing software. So I was at a talk in Cambridge not long ago, and they had the full FreeBSD, KDE, and everything running on top of that, on top of a CHERI computer, specifically the Armorello, which is an application class CHERI computer. CHERIoT is a Microsoft, was developed in Microsoft. It's built on top of the RISC-V 32 embedded ISA and targeting embedded applications. Yeah, I think that's everything I wanted to say. Awesome. So this is one of my favorite diagrams. Above, right at the top, that's the encoding. So I said a kind of hand wavy, there's a top and bottom and permissions. That's all encoded in a compressed form because the original CHERI had, for every pointer, you had your address and then you had a bunch of metadata. So it was like 4 words, which is very memory intensive. So they've compressed that all down into 1 word. So like the bounds are kind of got this floaty compression going on. But the most important thing is, the most important thing about CHERIoT is the kind of the monotonicity. So that's a fancy way of saying you can only ever remove permissions. So when you start up your core, you have at the top of this directed acyclic graph, you've kind of got these 3 core root permissions, and then you slowly strip away permissions to limit what things can do. A really good example of this is if you've got, say, a links list, and you want to, well, simple examples are read, write, execute, but then it goes into more complicated, nicer, more expressive examples, like if you've got read, write, if you've got, say, a linked list and you want to give someone an immutable reference to that linked list, normally you'd have the problem where if you gave them an immutable pointer, you strip the mutability, the right pointer from the top, then they could use the pointer and have mutability of the rest of the list. So you can take away the permission to load writable pointers from that area of memory, and then you've got deep immutability. Or one of my favorite examples, I really like Rust. Rust is a great safe programming language, but occasionally I have to call into C libraries and give them a buffer. What you can do is you can strip the ability to save that pointer into the heap so that when you call a C library and then it returns back to you, you know it can't have squirreled that pointer away from anything and you haven't broken any of Rust's safety rules, right? Because you're still the only owner with access to it. So loads of great features. There's also sealing, which allows you to give someone a pointer. Go ahead.
What happens when the C library tries to modify it? Is the code scratch or something?
Yeah, so something I've glossed over. Every one of these pointers has an out-of-bounds tag that says this is a valid pointer, right? Software has no way of adding this tag to stuff. So what happens, which is great for performance if you're a CPU architect, is the simplest thing you do is just remove the tag. And then it's no longer going to function as a pointer. So if someone tries to write to that top word, you remove the tag, no longer a valid pointer. And in this case, if the C library tried to store it into the heap, the pointer would be the tag would be removed to say it's not a valid pointer anymore. So it wouldn't be able to be loaded by any of the pointer load, well, do any load stores with it. Yeah, or you can error handle. So you get exceptions. So there's exceptions for any kind of load fault, and then you can handle the exceptions, see what happened, and work it out. It's not as nice as Rust, where it's all at compile time, but you can't do that when you're, calling binaries. But yes, and then they built a great operating system around this with mutual distrust. So normally an operating system, it's kind of a big monolith. They split it right out. You've got the switcher, which is the most privileged part, only a few hundred lines of code. Then you've got a scheduler, and that's just a normal compartment, only it's got access to the platform interrupt controller. Or you've also got the allocator, that's another compartment, only it's got access to a big hunk of memory that it can allocate to things. So nothing trusts anything else. It's like really nice from a security point of view, using all these tricks. For anyone interested in this stuff, I highly recommend the Programmer's Guide. It was done by SCI Semiconductor, David from SCI Semiconductor. I read it, I did the technical review of it, and it was a really easy read, very interesting. Even if you're not programming in this, it teaches you a lot. Okay, so onto the Sunburst project. The idea, what we were trying to do with this project is to get it into the hands of developers. So currently it's been an academic project, but it hasn't quite made the jump to industry. So we wanted to get it in the hands of engineers. So firstly, NewAE, who's a subsidiary of lowRISC, you might know them from like the security hardware they make for testing stuff, made an open source board. So this is open source. You can grab the Gerber files from here and make your own, or you can also buy one if you want to. It's got a Xilinx FPGA, RP2040 to do the programming. One of my favorite features is drag and drop. So if ever you've used the Raspberry Pi Pico, you can just, similar to that, you can just drag and drop the bit stream onto it. It pretends to be a FAT32 file system, and you can program it. It's also got like all the expansion headers. We've had file systems running on the SD card, Ethernet MAC, and 8 megabytes of hyper RAM, which is like DDR, but slightly easier to work with, so you don't need a whole DDR controller, which is really nice. Yeah, so we got that. That's one of the big outputs of phase 1. And we also built a system on top. So we got the CHERIoT Ibex, and then we built a system around it for people to use. It's also got a nice pin mux, so you don't have to edit the RTL. Well, the RTL is all open source, but you don't have to get the bit streams out, and we host them as releases on the GitHub page. But this has pretty much everything I've needed to do demos and tutorials, and loads of people. We've given about 125 of the boards out. Checking time. About 125 of the boards out, and loads of people have made some amazing demos with this. And we've got tutorials and stuff on how to play with CHERIoT. So it's been great. And then we've got a nice NICS environment to, yeah, a nice NICS environment where it all works. So this is kind of a platform for people to play. And then also, University of Oxford, some academics and students from the University of Oxford have formally verified the core. And it's an unbounded proof. So normally when you verify a core, you say this doesn't break any assertions for 100 cycles. This never breaks any of the assertions for however long it runs, which is awesome. They used new methodologies to put it together, and they also made it run fast. So it's only 4 to 5 hours to do a full formal proof of the core. Then we worked with them. We nabbed one of their students over summer and got that on the vanilla Ibex. So if you're using the latest vanilla Ibex, it's been formally verified, which is awesome. Apart from some instructions like the M instructions and some bits, but pretty full. Okay, then phase 2, in market availability. So this is great. You've made some amazing software that uses this, but you can't buy parts, basically. So we're trying to get parts onto the market. So we've worked with SCI Semiconductor, who've done a huge amount of the software work on CHERIoT since a lot of them out of that original Microsoft group. It's basically taking CHERIoT Ibex Core and a bunch of the OpenTitan peripherals and the verification infrastructure to make a production-ready silicon design. And SCI are using that as the base of their chip, the base of their design, which is going to be taped out later this year. So that's more. This is kind of open source based stuff. So they've got some proprietary stuff sitting on top of this. So it's not quite as open source as the OpenTitan chips that are coming, but it's pretty open source. The base is there, and you can take and play with it. If you want to build some CHERI SoC and you need a nice starting point. And then we also made a beefier Sonata board while we were at it, because when you're building silicon, everything gets a bit bigger. But yeah. Oh, and then this was a nice quote from the partner security architect at Microsoft saying, we did a good job, basically. But it's always nice to hear. Cool. And then CHERI Alliance. This is something I glossed over earlier. There's a new non-profit to kind of bring all the companies that are interested in CHERI together. As you can see, there's a lot of big names here. CHERI is very popular. I think it's almost definitely coming. The question is how fast and to where. But this is a coalition of people to get it there and to collaborate and have nice open standards. Currently, there's an effort to get a ratified RISC-V extension that's going through review at the moment. There's also, it's also free if you're an individual. So it's free for you to become a member if you're an individual and you want to learn more about CHERI. But yeah, do join. I think that's everything. So questions?
Thank you, Hugo. Are there questions? Yes, of course you want to make me run a morning workout.
You showed an example, 32-bit pointer. Does this apply to 64-bit RISC-V as well?
Yes, it does. So the ISA, the CHERIoT ISA, is very embedded, and it's only 32. This thing that's going through, that's going to be hopefully ratified soon, it has both 32 and 64 versions of it. So like a normal RISC-V extension. Then your pointers get big. Yeah, no, not 128 yet. Yeah.
Further questions? On the other part of the room, maybe. There's one.
What's up next for low risk and all this work? What are you guys planning?
Loads of stuff I wish I could talk about. It's one of those annoying answers. OpenTitan Project continues. Hopefully we'll get more tape outs and interesting stuff coming out of that. I'm hoping to get it more usable. There's a PR open to get it onto upstream FuseSoc and get it integrated in the rest of the open source ecosystem. So hopefully everything we're making is even easier to use. And then CHERI continues as well, but I can't say much more of that on both points, I'm afraid. But yeah, that's everything. Thank you very much.
Thank you. Hey, thank you.